Welcome to Chapter 12, number 37. This problem presents like a problem that we've seen before, the ladder problem, although this time, instead of it being at the top of the ladder, there's a roller that's here. And I think that it's a little challenging because you got to try to figure out what the roller means. It says the roller is frictionless, which means that it could slide either way without a problem. That doesn't mean it's not pushing on it though. The roller still, the uniform plank is still sitting on the roller, which means the roller is pushing it, and it's got to be pushing it perpendicular. So that's going to come in later. Before we start though, let's analyze this problem. Basically, what happens here is that if there weren't enough friction here, this would come out and this would come down and it would roll. And so it says at 70 degrees, the plank remains in equilibrium at any value that's greater than or equal to 70, but less than 70 it slips. So if this were any farther out, it would slip. So 70 degrees is the minimum, so we're going to try to find the coefficient of friction at the minimum. There's two things to do to start. One, there's a hidden geometry problem in this one also, which is really tricky and annoying. What we're going to need to do here is we're going to need to know how far up this plank does the roller push, and then we know the weight acts at the center of mass. So the first thing to do is we're going to have to, because it's a rigid object that's free to rotate, we're going to draw the force diagram, but we're going to draw the force diagram for the rigid object. I'm actually going to draw it up here because I think we might be able to do what we need to do up here. So here's the uniform plank. It's nice that it's uniform. Okay. We know the total length is 6.1. So what are some of the things that are pulling and pushing on it? Obviously, the weight acts at the center of mass. That is mg. It's in contact with the floor, so the floor is keeping it from sliding out. That's the friction. The normal force is also acting. Okay, we have that, and it's sitting on this roller, which is somehow above here, and the roller is pushing it perpendicular to, we're going to call this R for roller. So here's the forces, and because we have a statement like this where it's in equilibrium, we know we're going to need net force statements and net torque statements. So we can do either one first. I think it's easier to do the net torque statement first, so let's do that. Anytime you want to do a net torque statement, the first thing to do is choose the pivot point. Just like with the ladder problem, I think the easiest place to do the pivot point is down here. Oh. You could do the pivot here, you could do the pivot here. They're harder or easier depending. I think this is one we've done before. I think we should go with this one. Here's the problem. If I know that this is 6.1 the whole way, and I know that the weight acts here at the center, I don't know how far up this is. I don't know what this distance from the pivot point to the R is. So that's something that we need to find out. That's the hidden geometry problem. And what we can do is we can use this triangle right here, the way that I see it, to do it. Because I know that distance is 3.05. I know my angle is 70. What I'd really like to know is how far along this is. So I can just do it right here. Oh, this is meters. So this is the hypotenuse. This is the opposite side. So the sine of 70 degrees is equal to the opposite side, which is 3.05, divided by, basically, I'm going to call it d. It's the distance from here up to where the roller is. It's actually going to be my d here. So d is equal to 3.05 divided by the sine of 70. And I have d is equaling 3.25. Let me check that against my handy dandy calculator just so I don't make a bad error. 3.25, perfect. So this thing, it'd be 3.05 to get here because it's half of 6.1, and it's 3.25 to get here. So now I have a distance, so now I can write my net torque statement. So it's not accelerating at all, so the net torque has to be equal to 0. I'm using this as my pivot, so I have an mg. mg would make it go clockwise, so negative, and that's L over 2 mg times the sine. And if you look here, this would be the angle between the r vector and the mg. That's this angle here, so sine 20. The only other force which is the only torque is the r value here, or the r vector here. So that's going to be plus my d, that's the distance 3.25, times r, which is the roller force. Okay, not a radius, it's a roller force. And then times the sine, and we got to try to figure out what that angle is. Well, if I look, because it has to push perpendicular, my angle is actually 90 degrees. So sine 90. So if I look at this now, this is L over 2 mg sine 20 is equal to my d times my r. I know L, I know mg, I know the sine of 20, I know my d from here. I can actually solve for r directly. R is equal to 6.1 divided by 2 times m. It says in this problem, that the plank weighs 445 newtons, so the mg value is 445 times sine 20. Okay, and then to get that, we're going to divide all of this by my d value, which is 3.25. So when I go to calculate the r value here, okay, let me just put it in one more time, make sure I didn't make any mistakes. Let me check my notes, hold on. I got the R value is 142.8 newtons. So that's pushing this direction. So that's the net torque statement. That works out for us. But once we have the net torque statement done, then we still going to need some net force statements because we're not even close to the coefficient. Remember, the coefficient is the relationship between this friction and this normal, and we don't have a good sense of what either of those are. So let's do the net force statements. Let's do the x first. The net force in the x direction, obviously it's equal to 0, it's not accelerating. And what are our two forces in the x direction? Well, it looks like the frictional force is to the right, and what's to the left? Well, to the left we would have the horizontal component of the roller force. Therefore, what we're saying is the frictional force is equal to the horizontal component of the frictional force. Which is actually pretty interesting because if I look over here closely, Here's the horizontal component, here's the vertical component. You can see that this is the 70-degree angle here, that's 70 there, this is 20 here. So this is actually r cosine 20 degrees. And if I plug and chug that really quick, so this is 142.8 times the cosine of 20 degrees. It looks like we can get a frictional force value right away here. I got 134.2 newtons for the frictional force. So that's pretty cool. What about the y direction? What about the net force in the y direction? Well, if I look at this, what I can notice is that in the y direction, I have the normal force is in the up direction, the vertical component of the roller force is in the up direction, and the weight is in the down direction. This is also equal to 0. Therefore, if I want to find the normal force, it's going to be equal to the weight minus the roller in the y direction. But look at the roller in the y direction. The roller in the y direction is r cosine 70, or sine 20, it doesn't matter here. So if I want to solve for the normal force, the weight is 445 minus 142.8 cosine 70. Let me check that real quick. I have a value, but I want to make sure it's right. I got my normal force value is equal to 396.2. And now, in the end, what we're actually looking for here is the coefficient of friction. We know the coefficient of friction by definition is the ratio of the frictional force to the normal force. My frictional force is 134.2. My normal force is 396.2. And that's equal to 0.34, and it's newtons per newton, but they usually leave them off, so 0.34. This is, in my estimation, the easiest way to do the problem. If you use the roller as your pivot point, you can still do it. It just takes a couple extra steps. You could use the weight as your pivot point. It's going to take a couple extra steps. But all the principles are the same. You need a sweep picture, a force diagram, net torque, net force in the x, net force in the y, and solve, and you're golden.